Welcome everybody to my today's presentation. My name is Ronny Seinert and I'm working for the German company Eberle. And today I would like to present to you the results of a measurement campaign that we carried out in the year 2017 with the topic of simultaneous charging of electric vehicles and the evaluation of supraharmonics up to 150 kilohertz. First of all, I would like to say a few words about our company. We are a medium-sized company which is located in the southern part of Germany with about 100 employees. And now we have more than 40 years of experience in the field of measurement and regulation technology on all grid levels, so from low voltage to medium and high voltage applications. And our experience in Germany gave us the possibility, because of our contacts with the universities, to participate to such a measurement campaign where the goal was to find out which disturbances are produced by these newly installed electric vehicle charging stations. Here you can see the general setup of the test, which has been carried out directly at the University of Bingen in some kind of warehouse building. And on top here you can see the public grid connection with the 20 kilovolt medium voltage grid being connected to a main bus bar, and there was also a PV plant being installed at the rooftop of this house. And in the next level of this diagram, you can see that there are 3 connection cables with a length of about 25 meters, which are used to connect the charging points to the main bus bar. And you can see here at the bottom that it was like a grouped connection, always of 4 charging points with 32 amp connection. And there was also one measurement point with 2 63 amp connection cables. We used the measurement points at the main bus bar in order to evaluate the power quality according to public grid standards. And of course, we also used the measurement points in the depth of the grid in order to measure supraharmonic noise and the interaction of different vehicles during the charging process. And as I said in the beginning of this presentation, the main objective of this measurement campaign was the analysis of supraharmonic of high frequency disturbances to the grid. But of course, first of all, it is important to get an overview of the general grid situation in order to find out if the grid connection point is strong enough in general to be able to supply the charging power for so many electric vehicles. So first of all, we started at the main bus bar with just a general power quality evaluation according to the known grid standard EN 5160. And as you can see here in the diagrams below, we have seen no limit violations of voltage changes or THD imbalance or in the individual harmonics. And this information is showing us that the connection point itself has enough short circuit power to be able to supply all of the loads, and therefore we could now go deeper into the analysis of the behavior of the electric vehicle chargers. First thing we noticed when starting to analyze the charging currents and voltages on an oscilloscopic level was that we saw some different characteristics into the charging behavior between different vehicles. So for example, here on the left hand side you can see a normal charging current, which you will see from electric vehicles being produced by bigger companies such as Tesla or Renault. And you can see here in the charging voltage and current that they are almost perfectly in phase and have a quite sinusoidal shape with a little bit of a higher frequency on top, but we will go to this in detail in the later foils. And you can also see that the load, so the current level between the 3 phases is quite symmetrical. So this would be the ideal charging situation. But we also saw some electric vehicles who are retrofitted, which means that they were not originally designed to be electric vehicles, and somebody built in an electric motor and a charging unit. And at these vehicles, we saw some strange current forms, which you know from the industry. For example, here you can see a current shape which is reminding you to a B6 rectifier, like a 6-pulse unit. And at other vehicles, we found this type of current shape, which is more like a rectangular current, causing also a lot of current harmonic distortions, which stands for inductive smoothing here. And there was also one vehicle who was charging with a high power and a single phase mode. So here we had more than 35 amps on a single phase, with also some phase shift to the capacitive load, which is normally not allowed to be connected to a public grid, because you have to take care to symmetricize your loads. But yeah, at some vehicles there we saw this kind of strange behavior, but for the mass-produced electric vehicles, charging voltage and current looked generally like this. But there were also some differences when we had a look at the higher frequency disturbances here. Before going deeper into the analysis of higher frequencies, I would just like to describe something about the general behavior of the charging. And what you can see here is a diagram with voltages and current from the startup of the charging process from a Tesla. And you can see here that at the end of the startup process, the device is going to charge with 32 amps, 22 kilowatts. But you can see that it's not switching on directly from 0 amps to the full power. It's like cascading the charging process from line 1 to line 2 to line 3. First of all, to a stage of 16 amps. And after about 10 seconds, they go for the second stage at 32 amps. And of course, this is a little bit more friendly to the grid because you do not have this high current peak and you're not producing as much transients as you would do when you're directly switching it on. And you can also see here that it had some reactions on the voltage. So because of this imbalance that has been caused here, you can see the light blue line is the neutral current. We've seen some slightly over voltages during the first stage. And you can also see after the second stage that there is some steady state voltage drop just because of the consumed power of the charging station. This is also quite interesting, a complete charging cycle of electric vehicle who is charging with 11 kilowatts. And you can see here in the beginning that it's charging with a constant power. There were some short interruptions here. And at one point, the battery capacity reached a point of 80%. And from there on, the charging power has been reduced continuously, as you can see here. And there was also one point here where the charging changed from a 3-phase charging, symmetrical, to a single-phase charging. So you can see here that the blue and the green power is going to 0, and the red power is coming up to this line, and it's still decreasing. And you can also see, as I said before, the power factor is close to 1 because voltage and current are perfectly in line. But in this range here where the power has been decreased, you can also see some reduction of the power factor from 1 to 0.89. But of course, the main topic of this measurement campaign was the higher frequencies. So we also had a look at the charging voltages and currents in detail with our PQ-Box-300, which is able to analyze the frequencies up to 150 kilohertz continuously. And when you have a look at an oscilloscopic view with this high sampling frequency, you can see these high frequency ripples on top of the current and of the voltage. And just from the mechanics of how the distortions are spread, you can say that these high frequency currents are produced by the charging stations, and they are causing a disturbance level on the voltage just over the grid impedance of the connection point. When you're analyzing these type of frequencies, it makes sense to use an FFT analysis because this is transferring the signals from a time domain to the frequency domain. And here you can see a cutout of this complete FFT analysis between DC and 20 kilohertz. And everything you can see here on the left-hand side, this is what comes from the classical harmonics, what the EN5160 standard is evaluating. And everything here on the right-hand side, this is the so-called supraharmonic voltages and currents. And in this case that we saw before, we can see here that there was a current of about 400 milliamps causing a distortion on the voltage of 1.75 volts. And now, of course, the interesting part is how to evaluate this. Is it bad to have 1.75, or is it still below the limit of the grid? And in order to evaluate, it's not enough to do like a snapshot measurement. You have to do a continuous measurement of at least 1 day or 1 week. And this is a big benefit of PQ-Box-300, and I just want to show you some of the results here. In general, at the moment, there's only one grid standard who is regulating these higher supraharmonic frequencies, which is the IEC 61002-2. And you can see here an extract of the standard with the disturbance levels. It's a bit hard to read because they are defined in dB microvolts. So I placed a little hint here. So 120 dB is about 1 volt. So you can imagine that, for example, at 30 kilohertz, the limit value is about 1 volt, and it's dropping down to below 100 millivolts at 150, and this is how this limit curve would look like. And now if we take PQ-Box 300 and we make a measurement for 1 day, it is possible to make a statistical evaluation about the charging processes, and this is what you can see here. So this is a bar diagram. The red bars are showing the 95% value of statistical value. 95% of the values were lower than this, and the blue bar is showing the maximum value. And on top diagram, you can see these values in volts. So this was about 2.5 volts maximum. As you remember before in this diagram, during the snapshot, we had about 1.5 volts. So there was a time where this disturbance level was a little bit higher. And in the bottom diagram, you can see the same values as dB microvolt, and also with the limit graph from IEC 61002-2. And it's also noticeable that we had some minor limit violations here in the range of 80 kilohertz and 60 kilohertz, which is quite interesting to see. And as I started to explain in the beginning, we also tried to have a look at the interferences between multiple devices connected to one measurement point or to one charging point. And this is one effect that we saw here was that we had one single EV connected to a charging station, and you can see this little ripple here, which was being produced at a frequency of about 50 kilohertz, but the disturbance level was not very high and there were no problems into the grid. And sometime later there was a second device being connected to a measurement point in about 15 meters distance. And you can see now that the charging current of the first vehicle, we did not change the measurement point. We're still measuring at the first vehicle, but you can see on the charging current that now there is a very high disturbance on this current, which is coming from the vehicle on the other side. And this high disturbance here caused the first vehicle to stop charging, and it did not start again to charge until the other device was disconnected. And this has something to do with the general characteristics of supraharmonics in comparison to the general harmonics. So in general harmonic analysis, it is if you have two devices being connected together to the grid, they are going to produce a specific frequency, and the current with this frequency is going to flow through the grid impedance and cause a distortion here. And in the supraharmonics with the higher frequencies, the problem is, or the special thing is that all of these devices have capacitors inside, and the impedance of these capacitors is going to decrease with increasing frequencies. So the higher the frequency is, the more these disturbance currents tend to flow back to the other devices. And so you have like a current flow between the devices, And you will not see much of a current here at the transformer because the inductive characteristic of this transformer is going to damp everything down. Yes, all in all, I would like to just to give a little bit of a summary of these results here. We have seen no classical power quality norm violations during the measurements because short circuit power was sufficient for these charging stations. The EV chargers showed also different characteristics in voltage and current form, but all of the mass production electric vehicles had a clean sine and current wave except of the higher frequencies. We also saw some imbalances during the charging process, for example, when running up and also when reducing the charging power at high charging level. And we also saw supraharmonic emission violations if we compare it to the IEC 61022 standard. And of course, we could see some mutual interferences between electric vehicles. And we also saw these kind of interferences between the electric vehicle and the PV plant, which was installed at the roof of this building.